Hey guys, welcome back to the Transformer series, and today is part 2. So we're going to be talking about attention and encoders. If you've not seen part 1, I would suggest you go back and watch part 1 because it's a continuation. But even if you haven't, I'm sure you can understand part 2 even without it. So let's get right into it. Before we hop into the attention mechanism, I'm going to give you an analogy using databases. And you might be wondering, but why databases? Don't worry, I'll get right into that. But for now, I want you to keep everything aside and just focus on this part. So imagine you have a database where you have your student ID, which is your key, and you have some value associated with it. And here it's student name. Let's suppose you got a query. So your query, oh, excuse my handwriting, your query is nothing but, let's just say, select name from your table, which is this in our case, where id is equal to 101. What do we expect? So we expect it to return Alice, right? So that's nice. We've gotten an exact key match and we've gotten Alice, sorry. But what if it's not that simple? Let me show you another example. Let's say we have volume of ice cream. This is just an arbitrary example. And you have your price associated with it. What if you want to query 560? What if you want to know the price of this? So how are we going to query 560? Well, one thing we can do is, since there's no exact match, we're going to need some sort of weighted average, right? A weighted average. So we need to compare 560 with our given database, and then based on the similarity of the points, we decide the price value. So obviously, if you look at this, 560 is definitely closer to 600 as compared to 500. So we want to assign the weights in such a way that we give more priority to the closer points as compared to the faraway ones. So how do we do this? Let me just show you how we get this done. So first, let's calculate the distance. So the distance between 560 and 500. We're going to use the Manhattan distance. So the Manhattan distance is just defined as the absolute value difference between the 2 points. So by that I mean it's just simply 560 minus 500, which is 60. Similarly, we're going to find our point, our query, with respect to the other point. So this is 560 minus 600, and again absolute value, which is 40. Now what we measured here is distance. So we've measured how far a query is from a given using distances. But what do we want? As I mentioned earlier, we want similarity. And one way we can take similarity is simply by taking reciprocal of the distance. Again, I don't want you guys to worry about too much detail about why it's taken as a reciprocal and all of that. This is just for your intuitive understanding. So just know, like, obviously, the more far away the point is, the less similar it is, right? So there's an inverse relation, hence we're taking reciprocal. So we can define our similarity for 560 and let's say 500 as 1 over 60. Similarly, we can define the similarity of 560, a query, with 600 as 1 over 40. Now this is nice. We've gotten our similarity between the query and our points on the database. But there's a slight issue. The issue is these are not normalized. And we want, when we take our weighted average, we want them to sum up to 1, the sum of the weights, that is. So how do we possibly manage to do that? So one way is we can take percentages. We can find the total similarity and then get the equivalent percentages and take them as coefficients. That might have sounded as a lot of jargon, but once I write it out, I'm sure you'll understand. So let's find the total similarity. So your total similarity is nothing but 1 over 60 plus 1 over 40. And this is nothing but 100 over 60 into 40. So this is 100 over 2400. So this is your total similarity. Now we're going to find the percentage. So the percentage of, let's say, your similarity from from the point 500. So that's, let's look at that again. So that's 1 over 60 divided by 100 over 2400, your total, and into 100. So this, you get the percentage. So this is 1 over 60 into 2400 divided by 100. So we can just cancel this, and I forgot an into 100. We can cut, whoops, sorry about that. We can cut your zeros here, and 6 will go here 1, 6 will go here 4 times. So this is 40%. Similarly, we can find the percentage of this, of 600 with respect to your query. So that will just be 1 over 40 divided by 100 over 2400. This will just end up being 60%. So now that we've got the percentages, let's find the coefficients. We want them to sum up to 1. So again, here we've taken percentages, but if we just take 40%, so 40%, its equivalent is 0.4. 40% is just 40 by 100. So your coefficient will just be 0.4 and 0.6. So that means your weighted average, your value, so your weighted average, which is your price of your ice cream when the weight, when it's, sorry, not weight, when its volume is equal to 560 centimeter cube, is simply the weighted average. So that's just going to be 0. Let's just go back up 1 second. Yep, 0.4 into the value associated with 500 plus 0.6 to the value associated with 600. So that's nothing but 0.4 into 50 plus 0.6 into 60, which ends up working out to be $56. So we've got an approximate value we've calculated using similarity. So if we take our data set, our approximate value of 560 centimeter cube from our given data is $56. Now guys, you might be wondering why I spend so much time explaining a database analogy. Why did I do all of that? Now I'm going to blow your mind. What if I told you that when we calculated similarities and we got the weighted average, what if I told you this whole process is exactly what attention is? Can you believe that? Attention is just simply a weighted average. And in our case, we worked with single data points. But when we come to the attention mechanism, as you'll see, which I'll explain in a bit, is instead of working with scalar numbers, we essentially just work with vectors. So we use dot product to get the similarity. That's it. So this whole example is just attention. So attention is simply a weighted average. So now we're going to get into the code of the example that I've shown before, and we're going to see whether we get the same answers and how it works. All right. So we've got our schema. So we've got a name, a weight, and a price. So instead of volume, I've just named it as weight here, but essentially it's like the volume equivalent. I've just named it as weight. So the first function we've got is getDistance. So what does getDistance do? It takes in your new point, your query essentially, and it's going to compare it with your current data points and return the distances. And it's going to return it in the form of an array, and the orders will be preserved. We're going to code it in such a way it does get preserved. So we're going to need a distances list. We're going to be returning distances. So we want to compare our new point to all the other given ones. So our distance, if you remember the formula, is just the absolute value of our new point. We want to subtract our weight, which is essentially the volume in the given example, and compare it with this. And we simply just append it. Distances dot append, and we append the distance. Next up, we got a get similarity. So it takes in the list of distances, and essentially what it does is it returns, well, the similarity, and that's pretty easy. So we got similarity score. It's going to be a list. So we're going to iterate through it. So for distance in distances, we simply want to calculate the similarity, which is essentially just 1 over distance. And we just append it. Similarity score dot append and similarity. Easy. Oh, and instead of empty list here, we return your similarity score. Next up, we get the coefficients. So to get the coefficients, well, we're going to take in the similarity score, and then we're going to calculate it. So first, we're going to need the total sum. Let's first initialize your coefficients. Let's just name it coefs. So your coefs is empty, and your total similarity, let's just give it a 0.0. So for value in your similarity score, your total similarity is just going to be the sum with the value. And then we're going to do for value in similarity score, we're just going to append. So your coefs dot append, and we simply just append our value over the total similarity. We're going to keep this, and we will be returning the coefficients. Then for us to get the weighted average, well, that's going to be easy. We've got our coefficients. Let's get our coefficients. So our coefficients is going to be, we're going to get our coefficients, we're going to get our similarity, and we're going to get our distance from our points. You point at your data points, and we're going to name the price is equal to 0.0, and we're going to keep track of index and iterate over. We're going to iterate over the full length of data points, and our price is just going to be our coefficients of our index, and we're going to multiply it with our data points index dot price, and we're going to return price. Rather than naming it price, I'm going to name it the weighted price. Let's do that, and I can remove this. And for clarity, let's also print out and make sure everything is printed correctly or calculated correctly. So we're going to print distances. It's going to be distances. Then we're going to print our similarity. Let's do similarity. And our coefficients. It's going to be similarity score, sorry. And for our coefficients, we're going to just print them out again. So we're going to print coefficients, and we're going to print the coefficients. And here we've got the weighted price. And over here, I've got our data points. Let's first test with 2 data points, A and B. And we're going to print the weighted score and see if we get the same thing. So I am going to run this code. Let's do that again, but let me pipe it into output.txt, and let's check it out. And we've got it. We got it exactly what we wanted. Our distance is 60, 40. So a new point, let's just go back to this code. Yeah, we'll compare it with a new point, 560. And if we look at that, we got 60, 40. We got a similarity, 1 over 60, 1 over 40. Got our coefficients. And we finally got our value, 56. 56 is the weighted. And if we add a new point, we can just simply append it to this data point list. And let's do this, run the same code. And there we go. If we got 0.70, 700, our distance between 560 and 700 is 140. Then it's the same process. And when we have these 3 points, we can see that the value is 58.04 or 05 approximately. So this is how it's done with the code. Now let's move on to the next part. Before we head into the attention mechanism, let's look at the architecture of the encoder again. So we've got our positional encoding and input embeddings, which we covered in the last video and how we got them. So that gets fed into a multi-attention head. Then there's going to be normalization. And as you can see here, there is something called a residual connection. So this arrow here, this one, that goes from here to here. Let me just change the color. From here to here is called a residual connection. And then we move into a feed forward, and that again, there's a residual to it. So we're going to start with attention first. Once we finish attention, then I'm going to explain how multi-head attention works. So let's get into that. So now we're finally getting the crux, which is attention. I'm going to need you guys to focus with this one, because once you get it, it's going to stick with you. Trust me on that. So we got our attention. So let's take our sequence, Betty bought some butter. So our context length here is 4. So we got a query, a key, and a value, similar to the database analogy. That's why I taught you about that. And E of Betty, E of bot, E of sum, and E of butter represent just the embedding version of that. So technically it's the tokenization, and then the token ID has the corresponding this one. But here we're just taking word level tokens. So let's not get too much into the details. Let's just understand this part of this. So yeah, okay, so just know that E of Betty means the embedding corresponding to the word Betty. So we've got our context length of 4 and an embedding shape of whatever. Let's just take 12. Why not? So that means E of Betty is a vector of length 12. So here it's called self attention because each query is compared to itself. So ultimately, what do we want? We want a similarity score. So we want to compare Betty with bot, Betty with Betty itself, Betty with sum, and Betty with butter. And similarly for bot, we want to compare it with Betty. We want to compare bot with bot itself. We want to compare bot with sum and bot with butter. So ultimately, what do we need? We need a 4x4 shape. We want to compare each sequence with itself. So each word in the sequence rather, or token with itself. So ultimately we want a 4x4. So we're going to need the similarity in everything. And let me get into how that works as well. But before that, let's look at this. So we got a query, we got a key, and we got a value. Now we got the embeddings associated with those words, / tokens. But if you look at something, it's essentially the same thing. Your query, your key, and your values are the same embeddings. But we need to differentiate it. And one way we can help differentiating it is by multiplying it. So we can take our query. We want our input to be multiplied by a weight matrix WQ. So here, what it is your X is your positional embeddings plus your input embeddings, and WQ is a random weight matrix that is initialized using PyTorch and everything. So this essentially is done so that we can differentiate between the query, key, and value. So similarly, if Q is for the query, so we've got our key. Again, we're going to add X, and we're going to have a weight associated with that. Similarly for V, we've got X and WV. So what are the shapes for all of this? So your input shape is essentially just your context length and your embedding time, and your weight matrix will be embedding time, the dimension of your embedding, comma, the dimension of your attention head. So I'll explain what the dimension of your attention head would be when we do multi-head attention, but for now we can just take it the same as the embedding dimension. So you've got essentially your Q will be X, so we're going to take 4 as the length. We got 8 as the embedding time, so your WQ will have to be 8 by your head dimension, but in this case let's just take 8. So your Q ultimately will end up being 4 cross 8. So similarly for key, and then we've got the V for value. Now how do we get the similarity? Before we took the distances, we took the reciprocal and everything. But what do we do in this case? So in this case, to get the similarity 4 by 4, it's pretty simple. Since we're working with vectors, a brilliant measure of similarity is just the dot product. So we take the dot product of our Q. So this is your 4 comma 8, and we're going to take the dot product with respect to your key. But we can't just take key because key is also 4 comma 8. So we take key transpose. So it's 8 comma 4. So here we end up with a 4 comma 4 shape, which is exactly what we want. So this essentially is your similarity. And there's something that we do. I urge you guys to have like basic understanding of neural networks and batch normalization, because we're going to be applying some of that concept here. So we're going to divide this with the root of your dimension of your head, your attention head. So in this case, our dimension of our attention head is just 8. So it's just QK transpose by root of 8. Now, why do we do this? So we do this essentially to get our variance to be back to 1 at the output end. Again, I urge you to watch the neural network video where I'll explain exactly why that is and how initialization matters. But just know that this is to help with the stability when training. So we divide it by square root of the dimension of your head. Now the issue with this is you'll still have negative values and everything because it's just the dot product. Now, remember what we did last time? We took the percentage wise to get the coefficients right. So for here, how do we do it since we're working with vectors? Well, here we just need to simply add, let me just change this. Yeah, here, now that we've got our similarity score, which is just QK transpose divided by root of dimension of your head, to get it, the coefficients to sum up to 1, we simply just take the softmax of this. So we take softmax of QK transpose square root of dimension of your head. And here we've got the coefficients. Now what do we do? If you remember the database example again, now we need the value, right? We need the weighted average. So to get the weighted average, we simply take the softmax of your QK transpose by root of head. Let me just write that properly. Dimension of head. And we simply just multiply it with our value, V. And this is the output of your attention head. So your attention head essentially just takes in your input. Let me just erase this. No, actually, you know what? Let me just remove the stop part. And let's move this here. So your attention head takes in your input. So you've got your input embeddings, your input, it goes into an attention head. Let's name this attention head. And you get your output. And your output is essentially just this, your weighted average. And your output, whatever your input shape is, which will be context length by your embedding time, your output should always be the same, which is context by embedding. And here we can verify it because we know that this part right here is 4 cross 4. And we know this is 4 cross 8. And if we do the matrix multiplication, we ultimately end up with 4 cross 8, which was the same shape as our input. So this whole process, this weighted average and everything, is just attention. So now let's get into the code behind this. All right, let's start coding this. So I've got some boilerplate code here, and I've used a generator just that for reproducibility, nothing else. So we got a context length here, which is 4, and our embedding dimension, which is 6. So let's recall what we have to do. So one, we're going to need our input. So for our input, I'm just going to take a random array. So we're going to do tosh.random. Then we're just going to take the shape, which is going to be our context length and our embedding dimension. So we got our input x. What else do we need? Now we need our weight matrix associated with the query. So we're going to need our WQ. So that's just going to be a linear layer of our embedding dimension with our embedding dimension. And we're going to set bias as false. Then we're going to copy paste the same thing. But we're going to need this for K and V. So now we're going to calculate our query. So a query is equal to WQ of X. So this is essentially the equivalent of our X at the rate WQ, where at the rate is matrix multiplication. So this is a similar way of writing it. This is essentially the same operation. So we've got our K and we've got a V. Then we're going to get a similarity score. So similarity is nothing but Q at K dot transpose. And what are the dimensions that we're swapping? We're swapping, since this is zero indexing, so we have to swap the first and the second dimension. So we know that, sorry, this is not V, this is X. So we know that K is, the shape is context length and your embedding dimension. So your context length is 0 and your embedding dimension is 1. So when we transpose, we do 0, 1. So we're swapping 0 and 1. So we get K. So your K transpose essentially is embedding your embedding dimension, and your context length. You'll understand why we've specified 0 and 1 over here later. I'll explain it when we do multi-attention head. But for now, just know that this specifies which two dimensions we're swapping. Then we're going to need the square root. So here it's simply embedding dimension because that's what we need. Then we're going to take our normalized score, which is just going to be our similarity. We're going to softmax it over -1. So our output from the attention head is essentially just your normalized score at the rate V. So let's print our normalized score. Let's print our output shape. Let's print the shape of QKV, the shapes. So let's print the shapes associated with them. So it's going to be, I'm going to use an F string actually. So it's going to be Q dot shape, K dot shape, V dot shape. Let's put this in bracket. Oh, this ended up outside. This is supposed to be inside. And V dot shape. And let's see what we end up with. So I'm gonna run this. Looks like we got an output. Let's see what our output is. So we got our shapes, QKV, 464646, exactly what we need. We've got our similarity matrix, which is 4 by 4. And if you look at the rows, all of them sum up to 1. This sums up to 1. This sums up to 1. And yeah, this is essentially how it works. Now let's move on to multi-attention head. Okay, now let's move on to multi-attention head and how that works. So if you look at this, we've got our input X that gets fed over here into our multi-attention head, and we've got our layer normalization. Don't worry about layer normalization, I'll explain that next. But if you see this, you might be wondering what this batch size is. So batch size essentially is just a way for our GPU to process things parallelly. So we process our data in batches. So by doing that, what we do is all of that happens in parallel. So our GPU is really efficient at the parallel processing of this. So we just do it with batches. But when it comes down to the actual math, each individual batch just has your context length and your embedding dimension. So batch size is just to specify how many batches your data gets divided into, and it's just for easier calculations and faster calculations in the GPU. But like in terms of actual math, it does not affect anything else. So okay, so we've got our input, we've got that gets fed into our multi-attention head, we got a residual connection, we've got its output, and we've got layer normalization. So the output, again, I told you, should be the same shape as the input. So if you look at it, we've got batch size, context length, and embedding dimension. So if you have only one attention head, what we do is what we did in the previous example where I showed, where you have to end up with this. But here, if you look at it, it's embedding dimension divided by the total number of heads. So when we zoom in on a single head, this is what we get. And then we just concatenate all of our single attention heads. So we got embedding dimension by number of heads. So this is essentially what's called your D of your head. This is what we were talking about. It's your embedding dimension by number of heads. So we got all our single attention heads. We concatenate the output, and this is what we should get. This is the shape. And you might be wondering why there is a W0. Why didn't we just do this operation, which was just concat your head 1 output, your head 2, up to whatever, how many ever heads you have? Why did we not just concatenate it directly? Now the issue, if we just concatenate it directly, is that each attention head, okay, let me just show you something. Imagine that you have a picture. You got a person, you got the sun over here, you've got some trees. Now each attention head focuses on like a certain aspect. So let's say your first head focuses on the sun, your second focuses on the person, and your third focuses on your tree. So we've gotten the different attentions from each of the heads. Each of them paid attention to a different part of the data. But the issue is none of them have communicated with each other. So one does not know that two exists, two does not know that three, and like vice versa. There's no crosstalk between them. But we need that. So in order to have that crosstalk, what we do is we introduce a W0 matrix. So this helps essentially without crosstalking. So the dimension of this W0 is just your embedding dimension into your embedding dimension. And I told you we can ignore the batch size because that's just for efficient calculations. So your concatenation, you'll end up with a total of your context length star embedding. That's the shape. So again, matrix multiplication, this full thing ends up with the same shape of context length and embedding dimension. That's the shape of this full expression here, which is exactly what we wanted. We wanted our attention head to be the same shape as our input, as we mentioned earlier. So now let's look at the code version of this. All right, so here again, most of the code is actually going to be quite similar to the regular attention head, but here I'm going to be using classes, and it's going to resemble more of how it would look when you're actually doing this in production. So let's start coding. So we've got a lot of similar parameters as before, as you can see. But here we've got a class attention head. So we got our init method. So for our init method, what do we need? What does each attention head need? So each attention head needs to know what the embedding dimension is. So we're going to do that. And we're going to need to know the head dimension, which is just going to be head dimension. What else do we need? We need our WQ, WV, and WK. So I'm just going to copy paste this code. It's going to be the same thing, but I've got it written out. We can just, there we go. And now for our forward pass, what do we do? So a forward pass is essentially the same steps. So I'm just going to go back to the attention head. We're going to just copy this. Sorry about that. Let's move back. We're going to compute this. Then this is what we do. Most of the code is going to be similar. There we go. Let's fix this. Yeah, and here is going to be self dot. I'm going to name it self and self. And I'm just going to remove this. There we go. Now there shouldn't be any issue. Oh, need to import math as well. Let's import math. There we go. And we got our forward pass would just be we return our normalized code at the rate v. That's the output of our attention head. Now for our multi-attention head, what do we need? So we have our init method. So first we're going to need to initialize our number of heads, which is just the number of attention heads we need. We're going to need our head dimension. Our head dimension is simply just going to be our embedding dimension, and we're going to divide it by the number of heads. And now what are we going to do? We're going to need a bunch of attention heads. So a list of them. Since it's a multi-attention head, our embedding dimension and self.head dimension. And we're going to need to initialize enough for the total number of heads. That's it. And of course, the most important part, the cross-pollination, which happens with the help of our W0. So it's embedding dimension by embedding dimension, and we do not need any bias. So for our forward pass, what do? We need to concatenate. So our concatenate is equal to tosh.concatenate tosh.cat. We're going to need head dot forward of our input x for head in self.heads, and we're going to join it over the last dimension. And finally, here we're going to return w0 of our concatenation, which I told you, if you do this, is essentially just your concat at the rate w0. It's the equivalent. Now we're going to need our input, which I'm just going to copy paste the code. There we go. We're using a generator. And yeah, let's see the output that we get from our multi-attention head. Yep, seems to be working. And let's pipe this under output.txt. So we got our input shape, which is 4 by 6. We got an output tensor, which is also 4 by 6. We got 1, 2, 3, 4, 4 rows, so 4 and 6, 1, 2, 3, 4, 5, 6, which is exactly what we wanted. So this is just your multi-attention head. Let's move on to the next part now. All right, now let's move on to layer normalization. So right now I'm going to explain what exactly layer normalization is. I'm not going to be explaining the differences between layer and batch. I'm just going to teach you layer normalization. I encourage you to go look at the difference yourself. So this looks pretty daunting. I see the y is equal to x minus expectation of x over variance, root of variance of x plus epsilon. You might be wondering, hold on, what in the world are all these terms? Don't worry, I'll explain everything step by step. So expectation of x is essentially just your mean value. And here we got our variance. Here we have an epsilon term. I'll tell you why we need it. And then we got a gamma plus beta. This looks pretty familiar. If you guys know batch normalization, this looks really familiar to you. But here what we do is we calculate the mean and the variance with respect to the rows. So what I mean by that is, so for your sample 1, your mean value, which is just going to be 2 plus 8 plus 1 plus 5 over 4. So that's 10 plus 1, 11. 11 plus 5, 16. 16 by 4, which is just 4. And then we calculate our variance. So our variance is just going to be our summation of 1 over n. Your xi minus mu, the whole squared. So this is essentially just 1 over 4. It's going to be, so xi is just your data point. So it's summation. So it's going to be 2 minus 4 the whole squared plus a bigger bracket. Then 8 minus 4 the whole squared plus 1 minus 4 the whole squared plus 5 minus 4 the whole squared. So if I'm not mistaken, this should end up being around, let me just verify. You know what? Let's just do this ourselves. So it's going to be 1 over 4 divided by 4 plus 4, 4 plus 4 squared. So sorry about that. So that's 16 plus 9 plus 1. So that's 26, 30, 30 over 4. Let's just do that. So 30 over 4, which is 7.5. So our formula essentially boils down to our y is x minus 4 divided by root of 7.5 plus epsilon and gamma plus beta. So why do we need an epsilon? So we need epsilon. Epsilon is a very small number. I think it's 0.00001. Normally, that's what's taken. So we take this epsilon to ensure there's no zero division error. So by that, I mean, if all the data points were the same, if it was just 8, 8, 8, 8, our variance is just 0. But we can't divide by 0. So hence, to prevent the division by 0, we have epsilon to compensate for that. So yeah, this is layer normalization. I'm not going to show you the code for this one. I'm just going to show you the direct code when we get into encoders. But yeah, let's move on to the feed forward part of an encoder. All right, now we're reaching the end game. So after all the attention head and the layer normalization, as we can see here, we need something called a feed forward network. So what we've done so far essentially with the attention heads and the normalization and everything is that we've gotten our focus on our data set. We've gotten the different focuses, we mixed it up, we got the cross communication. So we understand what are the important parts, but we don't have the brain yet. So in order to introduce the brain that does the main thinking, we have a feed forward network. So a feed forward network is essentially just a simple neural network. So we've got our input neurons, then it goes into a hidden layer. All these are connected. And finally, we have our output layer. We're going to connect these up. Yeah, and all of these get connected. So I'm not going to show all the connections, but yeah, all of them do get connected. So what are the shapes going to be in this case? So again, over here, our input shape is, I'm going to ignore the batch size again because I told you batch size is just for computation. So it's going to be context length and our embedding dimension. And for our output, again, we want the same thing. We want our context length and embedding dimension. So our input shape takes in, is going to have, if our embedding dimension is say 384, so we're going to be 384 input neurons and our output will also be 384. And our context length is treated like a batch in this network. So this is why you need the basics of neural networks, because then you'll understand the batches and how everything works. And the activation here is ReLU. And these don't have any other activations. So this is essentially it. This is your feed forward network. And again, for this one, I'm not going to show you the code because it's essentially just a neural network. And I told you, as a prerequisite, this is, you do require to know neural networks and the code behind it. But don't worry, I'll show you like the main code when we hop onto encoders. And now we're finally reaching the end of the video. So we've essentially, whatever we've learned, now we just combine it, and that's your encoder. So we got our input. So your input goes into your multi-attention head. Then that, you got a residual connection that goes into a layer normalization. After that, that goes into your feed forward. And then again, that goes through another layer normalization. And this full box right here is called an encoder block. And then we just repeat that process multiple times. We got 2, and this should be 3, sorry, encoder block 3, and up to how many ever times you want to go through. And that's your encoders. That's it. Now let's just move on to the code for this, and we can conclude this video. And if you look at it, it's essentially going to be a lot of the same code, just with a few changes. So here we've got our feed forward network, hidden dimension. Our attention head's the same. We've got our multi-attention head. Oh, and mind you guys, this is not the proper full code. That will be covered in part 4. This is just for your understanding. I'll show you the proper thing and how NN modules work in the part 4 part. But for now, just take it at face value. So here we've got a multi-attention head. Again, the same working. Here we've got our feed forward. We've got the network that we've constructed. We use ReLU activation. And our encoder block is essentially just what we just showed. It's a bunch of the same thing. And the forward, yeah, you got self.layer plus x.self.attention. And then the second part after the feed forward, and we essentially return it. And your encoder is just a bunch of encoder blocks. And here I've got data to verify it. So let's just run this code and see if it works. Yep, it is working. So I'm just going to pipe this into our output.txt. And yeah, there you guys go. You can see it, the input shape, the output shape. And I recommend you guys to try and code this yourself because it's a lot of the same code, just a few nuances. But yeah, you can again look at my GitHub. I'm going to upload this code over there and you can test it out for yourself. So I hope you guys enjoyed this video. Leave a like if you did. And yeah, let's move back to OneNote. Give me a second. And with this, we have successfully wrapped up the second part. We're done with this. Now let's move on to part 3, which is your decoders and your outputs.